For chapter 8, you guys, for topic 8, let's look at 51 and 58. So rotational equilibrium and dynamics. 51 and 58 on that. All right. For 51, they talk about a light rod of length. So they're going to use moments of inertia for this, guys. This thing called moment of inertia. And we've already talked about it in class before this whole calamity struck us, struck the world for that matter. I mean, before things got as bad as they gotten, we talked about this stuff. We did go through here at least too. So there was this thing here. Vector quantity, the length of the rod, L, and this is M2, this is M1, here's the axle right here, so if that's L, this is L over 2, and this is L over 2 right there. And let's see what they're asking right here, guys. A light rod of length L equals 1 meter rotates about an axis perpendicular to its length and passing through its center, as in this figure. The two particles of masses M1, which is M1 is 4 kilograms and M2 is 3 kilograms, are connected to the end of the rod. A, neglecting the mass of the rod, what is the system's kinetic energy when its angular speed is 2.5 radians per second? B, repeat the problem, assuming the mass of the rod is taken to be 2 kilograms. If you bring the mass of the rod into it. So it's A and B. So let's take a look at that. All right, guys. Remember, look at the notes that we got right at the back of every chapter. There's an excellent book here. And it's in my notes as well, guys. They talk about when the mass of the rod is considered, if the rod did have a mass, its moment of inertia, I, is given by this mathematical formula, where L is the complete length of the rod. For A, when the rod is massless, that's another dynamic. When the rod is massless, the kinetic energy total is going to be the sum of the kinetic energies of what's going on. Well, the omega is the same for both. One's I1 omega squared plus, let me just see here, right, plus 1/2 I2 omega squared. So two different moments of inertia there, guys. Which is equal to, what's the moment of inertia? If it's a point mass, it's just M1 R1 squared. If it's a point mass, it's M2 R2 squared. So it's 1/2 got here, and they're telling us it's 2.5. So this is just the data they gave us. Remember, the rod is a total of 1 meter long. If the rod is a total of 1 meter long, the radius is half of that. Remember, we're talking about this. Each one of these is like a radius. This is R2, which is 0.5. This is R1, which is also 0.5. So that's kind of what we're using there. They're telling us it's the angular speed at which it's, the angular velocity at which it's moving. Grind out all the mathematics, you guys, and we're set. So there it is. I mean, at the end of the day, you're going to get this, the KE for rotation. .47 joules for A. What about the other one? Well, in the other situation, you're going to bring in one more player into this whole thing. You're going to say the KE of rotation here is going to be what you had earlier. Same exact thing we had earlier, not a problem. You got that. Plus 1/2 times the moment of inertia of the rod times omega squared. So basically what's going on here, guys, you got the 5.47 right here. And 5.47 right here, they're telling us, okay, what's the rod? The rod is, we'll go 1/2 times 1/12 is 1/24. The length of the rod, got to be careful on this one now. Centered as it is right there, through the center, I think they calculate this in such a way that you can do that. They're saying the rod itself is 2 kilograms. The L is the actual length, which is the whole length of the rod, which is 1 meter, and this is 2.5. Surprisingly, it's not a real big number, but it does add. If you're going to get it to go that fast, you have to put more work onto it to do it. It's got more kinetic energy. So there's one, there's the other. I mean, this is with the moment of inertia of the rod, because the rod is not massless in this situation. If it's not massless, you're going to have to give it more energy to actually get it to rotate the way the massless rod rotated, which means there's got to be more kinetic energy, more work done to get it to reach this kinetic energy. There's got to be more work done to get it to reach that kind of angular speed if you're bringing into account the fact that the rod has a moment of inertia. It's not massless. If you're getting a rod moving that's not massless, I mean, the moment of inertia of that item has to be accounted for. More energy is required to get it to go to the same angular speed as was required when the rod was massless. Massless rod, that's the kinetic energy. With mass, there's the kinetic energy. There's obviously a difference. Let's go to problem 58. 58, use conservation of energy to determine the angular speed of the spool shown in figure 8.58 after a 3 kilogram bucket has fallen 4 meters starting from rest. The light string attached to the bucket is wrapped around the spool and does not slip as it unwinds. So basically there's a bucket and there's a spool. The spool does have a moment of inertia, and from there you're going to figure out, again, their drawing is good. So look at their drawing, and let's see what happens. How does that all end up when they do that? What's going on here? Well, there's a lot going on. I mean, what happens with this, there it is. The spool's there. It's solid. It's a disc. It's solid. It's rotating. This thing falls. The mass fall, this thing's got a moment of inertia associated with it. This thing's a mass M. It's falling pretty far at that point. We don't know how fast it's falling, but what can we figure out what's going on here? So it's from rest, and a lot of this happens. Let me try to make this simple. So use conservation of energy to determine the angular speed of the spool shown after a 3 kilogram bucket has fallen 4 meters starting from rest. To find the speed of the spool, the angular speed of the spool. So we can find a lot of stuff, even stuff they didn't ask us to find out if we wanted to. We've got to determine how fast it's going if it's fallen from rest. It's fallen at some juncture. After it's fallen, you guys, it's going to speed V. I'll tell you what. I'll make it simple. We know how far if we know how far it's fallen, the energy's got to go somewhere. The thing fell at distance h. This guy. Don't worry about this guy yet. This guy's got a mass, and he's got a moment of inertia and everything else. I get all that. There's a moment of inertia there. There's a mass here. I get all that. Right now, let's say this thing started from rest and something happened. What happened? Well, this thing right here is the driving force to the whole thing, because, or at least the gravitational field that's on this guy is. This guy's going to fall a total distance of h. So mgh, all of that fall went somewhere. It went into rotational kinetic energy, and it went into the kinetic energy of the fall itself. Both kinetic energies got to be taken into account. That's the real big one right there, guys. This is the key to the whole problem. There's some other stuff we got to do. There's some other stuff that we got to do, but this is really the key right there. So with this right here, guys, let's remember a couple things. V equals omega times R, and that gets us through a lot of stuff, actually. And we also know that the spool, we can look it up, the moment of inertia of the spool is 1/2 capital M R squared, or small r squared, we're going to use the same R. Doesn't matter what R you use, doesn't matter what you call it, just be consistent with it. 1/2 mr squared is the moment of inertia of a solid spool. So if that's the case, you guys, this will be mgh, 1/2 of the moment of inertia omega squared. Heck, at this point, V is equal to omega r. V equals omega r, so it's 1/2 m omega squared r squared. Omega r is what this guy is, so we square it, you got that. Well, this is actually pretty damn convenient. What you get is, this right here is okay, it's pretty significant. There's a lot I can put together, a lot I can do here. I mean, you guys okay with this? I mean, omega squared r squared, which is v squared, that is v squared. What you gotta do is play some math, guys. So we got that. Look at it. Let me give myself a little more room. Let's knock this thing out. We can say here, guys. So we said let's see what we can say. I mean, based on what they're saying here, based on what they asked us, what are they trying to say here? How fast is it going, right? Hardest part of this whole thing is, or what's the omega associated with it? That shouldn't be too bad. The omega associated with it, you gotta just, there's a whole bunch of stuff you could do, I guess, to make this maybe a little easier to look at. Why don't you multiply both sides by 4? They don't like, because there's gonna be fractions all over the place, guys, so let me not do let me multiply both sides by 4. Multiply that by 4, you got this. Multiply this by 4, you got 2m, like that. And then you can solve for this guy and square root it. And what's going to happen is you're going to get omega squared equals 4 mgh over can be equal to this. Square root both sides. You know, I don't know, it's a horse apiece, you guys. I mean, you square root both sides, you got 1 over r. And the square root of, square root of 4, 2. Square root both sides. Square root of 4 is 2. And the rest is yeah, it's quite old school the way we did it. Didn't put any sort of actual numbers in there. We used this overt symbolism when we did this. So we can kind of look at it There it is. I mean, you plug in all the values that they gave you into here. That's that. That is for that one right there. So it's not looking too bad. That'll take us through 58. Okay. Let's go to topic 9. I'm still rolling right now. I'm still rolling. Let's go to topic 9, 43 and 88 for that one. For number 43, let's go to topic 9. And I think there's some really fascinating stuff in topic 9, Bernoulli's equation and things of that nature. Some things that really help us out regarding this stuff is whenever there's kind of any kind of fluid flow, and I have this solved for you guys in the handout, so you got it on Canvas as well. But if you were ever talking about something flowing like this, and this is obviously a big cross-sectional area right here. That's a cross-sectional area, A2, and the fluid is flowing at a speed V2 through here. And let's say this much is flowing. I mean, so that volume in a given period of time, that much volume is flowing. Down here, this, let me try to. The volume here of the water, the same volume is flowing at V1. This cross-sectional area is A1. This stuff is climbing from here to here. This is at, let's say this is the base height. This is the height Y1. This is the height Y2. So there's a lot going on here, but this very interesting formula known as Bernoulli's equation is pretty fascinating. It's just a ripoff of the conservation of energy. This volume right here, I probably confuse you more than I help you in that one. That volume right there is capital V2. This volume right here is capital V1. And it's the same volume for a given period of time. For any given period of time, the same volume is going through the pipe. Whatever goes in comes out. Now they're shaped differently because the pipe is shaped differently. Here, the particles aren't moving that fast. Here, they are moving real fast for that given period of time. The volume is the same in both instances. How much fluid flow rate is there? Well, we can call Q fluid flow rate. The amount, you see different numbers here, how this is written. The fluid flow rate is volume divided by time. Isn't volume cross-sectional area times length divided by time? If you divide the length by the time, the length of the little column, the length of the parcel divided by time, length divided by time is velocity, or magnitude of velocity. The volume flow rate you guys, is area divided by speed. So area divided by, area times the speed will give you the volume flow rate. And if it's a pipe, you guys, A1 V1 equals A2 V2. How could they be different? Whatever goes into the pipe comes out of it. If I got 100 gallons per minute going in, 100 gallons per minute are going to come out. You know, so Q1 equals Q2, the volume flow rate, and you got something like this. So there's a lot happening here. Well, yeah, it sure is. We know that the flow rate of mass is if you took the mass density times the volume and divided it by time, you get rho A1 V1, you know, the big volume, and that's speed right here. You're getting something like that in regard to that. Okay, there's a lot here, guys. I don't know, I'm not sure exactly. There is never enough time in these circumstances to do this the right way. So I'm going to try to do it in some way. You guys all remember that location and speed. So let's see here. Forgive me here, guys. I'm just kind of... Okay. So what we have here, guys, all right. Okay, so looking at this, I mean, there's some interesting stuff that goes on here, guys. Bernoulli's equation kind of gets us there in the sense that I've written a bunch of stuff here that might make sense to you, might not. But let's talk a little bit. This mass parcel here is identical to this mass parcel there. True, I mean, it really is. And the mass of the parcel, the volume is the same and the mass is the same. The mass is rho times V. And we could say a bunch of things here. Energy is conserved. Let's say there is some work that you've done here, work one. And there's some work that's being done on the other, there's some opposition to that work, and that's work two over here. It's kind of fighting the whole process. The difference between the two is what's gonna transpire. I mean, you're gonna say work one is a lot of work. Work two is not a lot of work, but it's something. The difference between the two is going to create, you know, there's a lot that's going on. The difference between the two is going to give you the difference in kinetic energy in two locations. So it's going to be 1/2 mass. Let's say it's going really fast in the beginning and not as fast up top. Now that kind of makes sense. We said that this guy's a small velocity, this is a big velocity, and you know, so we said that. And we said the difference between the two kinetic energies, the difference between the two kinetic energies is the same as the difference in the work that's there. And on the other side of that, the difference in the potential energies would be, let's see here, there'd be mg y1 minus mg y2. So it's pretty interesting how that all works out. I mean, in other words, what would create the differences here? This is not really it's probably a little better way to write it. It's essentially this is what you are going to write, but let me just see here. Let me see what else I can say.
Okay.
All right, guys. Let me kind of start it over a little bit. W1, that's visible, right?
Yep.
W1 is more work than W2. The difference between the two will tell you a bunch of stuff. We'll tell you, well, the difference between the two will tell me, okay, well, what all happened here? There was 1/2 mass, velocity 2 squared, minus 1/2 mass, velocity 1 squared. Plus, in other words, the difference in the kinetic energy, kind of see how I can write this here, and the difference in the potential energy too. All right, guys. I mean, so if there was work being done, some kind of work opposing the flow of the water, some kind of work W2 opposing, the water's flowing this way, upward toward your right. If there's some work W2 opposing that flow, and there's a work W1 trying to facilitate that flow, W1 beats out W2. It's a bigger number. So W1 minus W2 is going to be a positive answer, and all this is going to happen with the work that's being done. So when you look at it, you look at W1 minus W2, and I've got all this. I want to kind of just, you'll see where I'm trying to go with this in a second, I guess you could say. The way we would write it is, okay, guys. So what is happening here with that? So from here, why don't we just put all the 2's together, all the 1's together, and figure out what's going on here? And we end up getting W1 plus, let's just get them all over to one side, 1/2 m v squared mgy1, and here we got W2 okay, sounds good. Work is force times distance. True, but it's also, I mean, we can also kind of say on the side here, this thing called pressure is force over area. If you multiply it by volume, you got this right here. Keep going with that. The A's cancel, you got F times L. F times L, that's work. So there's something of interest here. I can, you can write this thing a lot of ways here, but here's one way to write it. I mean, pressure pressure is really work density. Pressure times volume will give you work, because F times L right here. So pressure times volume will give me work. Okay, well, let me say this is pressure 1 times volume 1. And let me say, for something like this, let me just keep doing that. So let's just, for those right there, let me kind of make this easier, guys. My finger is kind of injured right now. I've been writing forever. Christian can kind of attest to it. I'm sorry, it's actually bleeding, so I'm going to have to figure out how I'm going to finish this out. But that is life. All right, so let's do this. If you take this and you divide by volume, everywhere. Guys, what's mass divided by volume? What's mass divided by volume? Mass divided by volume, mass divided by volume. Well, mass equals rho times V. Rho equals mass divided by volume. If work is pressure times volume, if you divide by volume on each side, pressure equals work divided by volume. Well, work divided by volume is pressure. Mass divided by volume is density. Mass divided by volume is density. Work divided by volume is pressure. Mass divided by volume is density. This right here, it's just that all of this reduces to, comes out to, that's Bernoulli's equation. It's a rip-off of the conservation of energy. My notes discuss it probably a little bit better. It's like the multicolored Jim Malis approach when I do it with the notes. But all this came from was, this was W1 plus 1/2 m v1 squared plus mgy1 or mgh1. And this is W2 plus 1/2 m v2 squared plus mgy2 or mgh2. If you divide by volume on each side, the mass was the same in all instances. Why? Because the volume was the same in all instances. Didn't we say earlier? Big V1, big V2, big V1 equals big V2 equals the volume. It's the same volume mass. Everything that comes into a pipe goes out of a pipe. Everything going into a pipe comes out of a pipe. 10 kilograms of fluid flow every second. At the beginning, there's 10 kilograms of flow. And at the end, when it comes out of there, it's 10 kilograms of flow every second. If it's 10 kilograms every second in the beginning, it's 10 kilograms of flow every second at the end and in the middle. So they stay all the way through. Now again, the book has good coverage of this. I got it as well. But that's kind of the poor man's definition, I guess you could say. The poor man's derivation of what's going on with this. So this is going to help us solve some of these problems that we're doing. That's our goal. So let me erase that. Let's knock out those two, and let's see what we can say. And I'll see how I can try to give you some insight on this. If things get bad enough, guys, and we do got to take off, so I don't have a lot of time. My coworker and I, we don't have a lot of time. If we got to go, we got to go. You do have all this stuff, and it is fully solved for you. Okay, it's not like I'm throwing you to the wolves. You do have it. Let me see what I can do. Let me do the best I can do.